Swayam Prabha. Digital India. Educated India.
I welcome you all to lecture number 27 on the topic convection mode of heat transfer. Let's have a quick recollect on what we have discussed in lecture number 26. Lecture number 26 we applied the Fourier law of heat conduction for a composite wall, which is nothing but a multi-layered plane wall, in which if we know the individual resistance in series, we can find out the individual resistance and add all the resistance. We will get to know the total resistance. So, the Q value can be found by the ratio of delta T to the total resistance. In case if we have a parallel wall, layers or parallel wall, so we have to find out the equivalent resistance and add with the other resistance of the wall which are connected in series. And we have solved some numerical questions based on this topic. And there is one limitation when we use the concept of thermal resistance, that is, it is limited only to heat transfer problems which involves steady state condition and not for a unsteady state condition heat transfer problems. Now, let us see the contents of this lecture number 27. Introduction, then we will see the types of convection, natural and forced convection, some non-dimensionless numbers, that is Reynolds number, Grashof number, the governing law for convection, boundary layer, and the concept of boundary layer, which is very important. There are two types of boundary layers, velocity boundary layer and thermal boundary layer, and a few numerical questions. So, to begin with, the convection, it is a heat transfer mechanism which occurs due to the movement of molecules in the fluid. If we say conduction, that is due to the vibration of the molecules, and this is due to the movement of the motion of the particles, motion of the molecules. It is between a solid surface and a fluid. The fluid can be gas or liquid. Both the conduction and convection requires a medium for the heat transfer to take place. Of course, in both the cases there should be temperature difference, the driving force. If there is no driving force, then there cannot be heat flow. And this convection, the convective heat transfer, it is associated with the fluid mechanics, like some of the properties like viscosity of the fluid, all these things, and density. So, it depends upon the fluid properties such as dynamic viscosity. There are two types of viscosity, one is dynamic viscosity mu and kinematic viscosity nu. Okay, so, the ratio of dynamic viscosity to the density of the fluid, that will give the kinematic viscosity. Then the convection, it depends upon the Cp value, thermal conductivity and fluid velocity. It also depends upon the geometry and the roughness of the surface, okay, on which the fluid is either passing over it or into it, external flow, internal flow, etc. And we will see about the difference between the natural convection and the forced convection. This schematic depicts the difference between the natural convection and the forced convection. The other name for natural convection is free convection. So, as the name indicates, natural, the process takes place naturally without the support or aid of any external source, external device. So, here I have taken, there is suppose if the surface is maintained at a temperature 100 degrees centigrade. So, the same 100 degrees centigrade, there are two surfaces. So, on the left side, the picture represents the schematic represents the natural mode of convection. So, you can see the air is rising. Let us assume that the ambient is at 25, the same temperature that is there. Okay, so, here there is a surface, a heated surface, which is whose temperature is Ts is greater than Ta. So, we know when we heat a fluid, it becomes it becomes lighter. So, due to the density difference, so the hot one will rise up, hot fluid will rise up. Okay, so that is, this purple color indicates the hot air which is rising up. Let us take this as the surface as a plate which is heated. So, when the molecules of the air which are close to this one, it gets heated up and it rises up as it becomes lighter due to the density difference, density gradient. This process takes place. Whereas in case of the forced convection, as the name indicates, a device is used to make the air, to make the process, okay, to make this. So, in this case, a fan is used to circulate the fluid. The fluid is the air. Okay, so if we do the convection with the help of a device, a fan with an external device, so it is called forced convection. And if it takes place naturally due to density gradient, density difference, then it is termed as free convection or natural convection. And once, if we vary the velocity according to this fan speed, the velocity of the air changes, then the rate of heat flow also will change. Will change. The governing law for convection is Newton's law of cooling. For the conduction, it is Fourier law of heat conduction, Q equal to minus Ka dt by dx. So, the Fourier law of Newton's Fourier law of conduction, Fourier law is for governing law of conduction, and Newton's law of cooling is the governing law for convection. So, it states that the rate of heat transfer due to convection is directly proportional to the temperature difference. So, Q is proportional to, of course, the area of the configuration remains constant. So, into delta T. So, to remove this proportional term, a constant is introduced, that is called, in convection it is H, in conduction it is K. That is, in conduction the constant of proportionality is thermal conductivity of the material of that particular configuration, whereas in convection it is heat transfer coefficient. The heat transfer coefficient, if you see, if you divide like if the rate of heat flow is for 1 meter square area. Okay, so Q divided by delta T is nothing but H. Q divided by delta T, Q heat transfer per unit area divided by delta T will give you the heat transfer coefficient. So, HA into delta T, this is the governing law. HA into delta T is temperature. In the example which I have explained, the surface temperature is more than the ambient. So, Ts minus T infinity. Where H is the convective heat transfer coefficient or convection heat transfer coefficient in watt per meter square degree centigrade or watt per meter square Kelvin also, it is correct. Heat transfer surface area in meter square. Yes, Ts is the surface temperature and T infinity is the fluid temperature. Okay. There are two dimensionless numbers which we will be seeing in this lecture. The first one is the Reynolds number. This Reynolds number govern the forced convection, because when I say this one, it is the number used in forced convection analysis. Okay, so what is this one? It is the ratio of these numbers already you might have studied in the fluid mechanics. Let us recollect it. It is the ratio of inertia force to viscous force. That is basically the Reynolds number is about. So, if you substitute the formula, you will get Reynolds number. So, rho V L by mu, Okay. So, mu by rho, mu by rho is equal to, let me write it here, kinematic viscosity nu is equal to dynamic viscosity. When we say viscosity, it refers to dynamic viscosity, but if it is kinematic viscosity, we have to mention the term kinematic. So, kinematic viscosity divided by, I think there is, let me write it clearly, dynamic viscosity VIS divided by density of fluid, So, in terms of formula, this is equal to mu divided by rho. The ratio of dynamic viscosity to density of the fluid is called the kinematic viscosity. So, here I have got rho by mu. So, that becomes 1 by kinematic viscosity. So, that is V into L I have kept as it is. Okay, this term is as it is. So, if you know the dynamic viscosity and density, we can use the first formula to find out the Reynolds number. If we do not know the density of the fluid and the dynamic viscosity or the viscosity, but if you know only the kinematic viscosity, okay, if any two properties are known, we can find out the third property. But if these two properties are not known, but the kinematic viscosity is given, then we can use this one. So, where V is the velocity of the fluid meter per density kg per meter cube, kinematic viscosity I have given the units, and also similarly the dynamic viscosity. So, in case of free or natural convection, Grashof number is used. We cannot use the Reynolds number in case of natural convection, because in forced convection the velocity of the fluid is a very important parameter, whereas in case of natural convection, though there is the movement of fluid which takes place naturally, but when it compared to the velocity with which, or the when the fan is circulating the fluid, so it has got a very high velocity compared to the natural one. And this is the ratio of buoyancy force by viscous force. The inertia force is replaced by the force of due to buoyancy, and if you substitute and derive, okay, so you will get this is small g into beta into delta T into L cube by kinematic viscosity square. G is the acceleration due to gravity, beta is the coefficient of volume expansion, beta equal to 1 by T, beta equal to 1 by T, beta is nothing but 1 by temperature. This temperature should be in Kelvin, this is in Kelvin. So, when we are finding the beta value, we should not substitute the temperature in degree centigrade, it should be in Kelvin, okay, K power minus 1. Surface temperature, fluid temperature, length of the plate. Suppose instead of a linear configuration, suppose if you have a cylinder or a sphere, if you have a radial component, so L should be replaced by diameter, L equal to D. So, that is what I have given here. Okay, suppose if you want to find out the Reynolds number for a flow over a cylinder or sphere, so here it will be V into velocity into diameter divided by kinematic viscosity, or density into velocity into length, instead of length you have to put diameter, okay, of the pipe or tube divided by dynamic viscosity. Okay. So, now let us come to the concept of boundary layer, it is a very important one. So, here I have considered a flat plate, okay. So, whose there are two diagrams. First diagram is pertaining to velocity boundary layer, the other one is the thermal boundary layer. Let us take this temperature as Ts, this temperature as the surface temperature at Ts, U infinity, okay. This is the free stream velocity with which the fluid, okay. So, let us take air as the fluid here. So, this is passing over a flat plate whose surface temperature is Ts, What happens when the fluid is passing over the plate? When it comes in contact with these, okay, at the point of contact, when it is passing over this one, so it will be contacting the surface of the object or the plate, okay, surface of the object or the plate. So, at that point what happens? Because the plate is stationary, the object is stationary, there is no motion. So, the velocity of the fluid at that point, at the point of contact on the surface, becomes 0. Or if the plate is moving slowly, the velocity of the fluid at that point of contact will be equal to whatever the velocity with which the plate is moving. Because the plate is stationary here, so the fluid particles, the velocity at that surface, at the point of contact on the surface will be equal to 0. So, if we take the fluid as different layers, so this is the bottommost layer which is in contact with the surface, where this due to the friction between the between two layers, so that will reduce the momentum of the next layer, that second layer will reduce the momentum of the other layer, and so on and so on. Momentum is nothing but mass into velocity. However, there is a velocity gradient which will build up from the 0 velocity, that is at the surface, to a height or in the direction normal to the flow. The flow is taking place in this one, the normal to the flow is the perpendicular direction. So, up to a particular height, okay, up to a particular height, there will be a variation in the velocity. At one point in the direction normal to the flow, the velocity of the fluid at that point will be equal to the free stream velocity, and there will be no further velocity gradient. There will be no further velocity gradient. So, when we join all these things, you will get a curve like this, a line like this. This one refers to the boundary layer, this one refers to the boundary layer, and this delta refers to the thickness of the boundary layer. Delta refers to the thickness of the boundary layer. This is the velocity gradient. This is the velocity gradient. This is the velocity gradient. And after this point, there is no velocity gradient. And we know there is a correlation which connects the viscosity and the shear stress. Shear stress tau is equal to mu into du by dy. Tau is the shear stress, mu is the dynamic viscosity or viscosity of the fluid, which is into du by dy. That is, this is the velocity gradient. Change in velocity with respect to the distance, not the horizontal distance, in the direction normal to the flow, in the direction normal. So, that is why I have taken dy. So, this is dx, this is dy, this is x, this is y. Okay. And we know by Newton's law of viscosity, tau is directly proportional to the velocity gradient. This you might have studied in the fluid mechanics subject, du by dy. So, to remove the proportional term, a proportional symbol, a term is introduced, that term is the viscosity. So, that is how we got this equation, and this is the viscosity term, this is the viscosity term. So, once there is a velocity gradient, so obviously there will be a built up of shear stress. Shear stress, this is what Newton's law of viscosity, shear stress is directly proportional to the this one. Okay. So, this delta is the thickness of the boundary layer. Okay. Above this point, there is no velocity gradient. So, at this point, once it attains once there is no further velocity gradient, the velocity of the fluid will be equal to the free stream velocity. This is free stream velocity, free stream velocity, and the point of contact on the surface where the fluid velocity becomes 0 or reduces to 0, because initially as it was passing over the plate, it possesses some velocity. Only at the point of contact on the surface, its velocity is 0. That term, that is called as no slip condition. No slip condition. When the fluid over a flat plate, the fluid layer which is in contact with the flat plate sticks to the surface. This is very important, which is the fluid layer which is in contact with the surface, which is not just passing over the surface, the layers which are in contact, it gets stuck to the surface and there is no slip. So, this concept it is named as no slip condition. And velocity boundary layer, the region of flow above the plate, that is in the direction normal to the flow. Flow is like this, direction normal to the flow like this. Above the plate, bounded by the thickness of the boundary layer, in which the effects of viscous force, that is tau equal to mu into du by dy are experienced. So, that portion is called the velocity boundary layer, and the fluid velocity varies from 0, which is at the point of contact on the surface, okay, that is at the that portion is called the no slip condition, up to a certain distance in the vertical direction, that is in the direction normal to the flow. Okay, so the velocity varies from 0 to almost free stream velocity. It is 99% of free stream velocity, which can be taken as 100. Now the same diagram, and there is one more information which I would like to say, and here if you see there is laminar, turbulent and all. So if the Reynolds number, this is for an external flow, if the value of Reynolds number is less than 5 into 10 power 5, okay. Again let me emphasize, this value is applicable only for external flow over a plate, over a cylinder, not an internal flow. Okay, so this is external flow. So then the flow is categorized as laminar flow, and if Reynolds number is greater than 5 into 10 power 5, it is called turbulent flow. Okay, so this is external flow. Let me write it. This value is not applicable for internal flow, external flow. And the region which separates the laminar and the turbulent is the transition region, where the Reynolds number will be equal to 5 into 10 power 5. And here the flow is a smooth and an orderly one in case of a laminar flow, and in case of a turbulent flow it is not a smooth, it is a highly disordered motion. Okay. Now let us see the thermal boundary layer. So here, like a velocity gradient, if there will be a temperature gradient also. Temperature, of course, whatever may be the mode of heat transfer, there will be a driving force for the heat flow to take place, otherwise there is no heat flow. So this is the like a free stream temperature, instead of a free stream velocity, this is a free stream temperature. Okay, so this is free stream temperature. Okay, so this is the thickness of the thermal boundary layer. This T refers thermal. This T refers thermal. In the previous case, it is delta. If you want, we can refer as delta V, but most of that the standard textbooks use the symbol delta. Delta means thickness of the velocity boundary layer. Delta T means thickness of the thermal boundary layer. Okay. So here also the at this point, okay, so there is a the temperature is this one. As you move T minus Ts, temperature at any point minus Ts will be equal to 99% or which is close to 100% of this temperature, T infinity minus Ts. Okay. So suppose if Ts is small, the value of Ts is small, both sides will get negative value, which will minus sign, which will get cancel, or you can write Ts minus T infinity, Ts minus T also. Okay, so does not make any difference. So here also up to this portion only, there is a temperature gradient, beyond which the temperature of the fluid will be equal to the free stream temperature. That is what the temperature at this point, it will be equal to T infinity. Okay, so the temperature of the at this point will be T equal to 100, T will be equal to 99% of T infinity, which is nothing but T equal to Ts, So the thermal boundary layer is developed in a fluid at a specified temperature, okay, at a specified temperature, flows over a surface that is different, that is at a different temperature. That means there is a difference between difference in temperature between the fluid, the surface temperature and the fluid, which is flowing with the free stream temperature. The flow region over the surface in which the temperature variation in the direction normal to the surface, that portion is called thermal boundary layer. Okay, so that is the flow region over the surface. This is the surface temperature maintains Ts. Flow the region over the surface in which there is a delta T, there is a variation in the temperature, that is in which there is a temperature gradient. Previous case it is velocity gradient, this one is temperature gradient. So this portion is known as the thermal boundary layer, whose thickness is represented by the symbol delta suffix T. The thickness of the thermal boundary layer at any location along the surface defined as the distance from the surface at which T minus Ts is equal to 99% of T infinity minus Ts. And one more thing, this is called the leading edge of the plate, this is called the trailing edge of the plate. Okay. This is called the leading edge of the plate, let me write it here, this is the leading edge of plate and this is the trailing edge of the plate, trailing edge of plate. The boundary layer builds up from the leading edge of the plate to the trailing edge of the plate as the fluid flows in the positive x direction. So, with this background, let us solve some numerical. Okay, so before solving this numerical, let me take few time like maybe 5 to 10 minutes to quickly go through the two problems which I could not solve due to time constraint in the previous lecture. Okay, so let me, we have seen up to this point, we have evaluated the Q value, for the double pane window, that is the window which consists of two layers. The first layer, if you see if you remember the problem, this is the glass layer, then there is a air space, the air space separates the two glass layers. So, there are 5 resistance involved, left side that is RA, convection into the wall, then there are 3 conduction term, layer 1, layer 2, layer 3, then convection from the wall, Okay. So, we have solved this problem and we got there is a reduction in the heat flow from previous one was 266 watts, if you remember the one which we took as the previous problem. So, there is a reduction in the Q due to the change in the resistance, the total resistance of the composite wall. Now, because of which the temperature also changed from minus 2.2 degrees centigrade to 14. This is a desirable temperature because when we have a negative temperature, there are chances of fog formation, especially when the humidity of the air inside the room increases. So, this is the problem and there is one more problem which I could not solve it. So, let us quickly go through it. In a composite slab as shown in the figure is in the next slide, the temperature at the interface between the two materials is equal to the average temperature at the two ends. Assuming steady state one dimensional heat conduction, show that thermal conductivity of layer 1 is equal to twice that of layer 2. So, this is the schematic. Okay, so, there are 2 layers. So, here of course, here there is only, they have considered only conduction because if HA and HB, TA, TB is not given, then the convection heat transfer can be neglected for that particular numerical question or the example. So, we can solve by calculating only the conduction resistance of that particular configuration. So, this is the thickness, K1 is the thermal conductivity of the first layer and K2 and T1 to T2, there is an intermediate temperature. This is the intermediate temperature, this diagram is given. So, I am taking the interface temperature as T1, okay. Ti. So, there are slab 1, this is slab 1, this is slab 2. Okay. So, if you see there are 2 slabs, this is slab 1, this is slab 2. Okay. So, the Q through slab 1 will be equal to Q through slab 2. You have to find out the intermediate temperature. Okay. Intermediate, I think we have to find out, we have to prove that thermal conductivity of 1 is equal to twice the thermal conductivity of 2. Okay. To prove K1 is equal to 2 times K2, that is thermal conductivity of the material slab 1 material is equal to twice that of the slab 2 material. And there is, it is clearly given the temperature at the interface between the two materials is equal to the average of the temperature at the two ends. The temperature at the two ends, on the left face it is T1 and on the right face it is T2. So, it is given that interface temperature is equal to T1 plus T2, that is left face temperature and right face temperature, the average. So, divide by 2. Okay, so, heat flow through slab 1 is equal to rate of heat flow through slab 2 under steady state, under steady state, Q of slab 1 is equal to slab 2. So, it is like in slab 1 it is from T1 to Ti, slab 1, and from slab 2 Ti to T2. Okay, so, let us quickly so apply this one K1A into T1, apply the Fourier law of heat conduction, Ka T1 to Ti by, here it is 2b, see the thickness of slab 1 is 2b, thickness of slab 2 is b. So, let me write also that also, L1 is the thickness of slab 1 and L2 is given as b. So, if you apply the basic equation, and also we have to substitute Ti is equal to T1 plus T2 by 2. Okay, so, that is what I have written here, K1 I have just written, this is Q of slab 1, this is equal to Q of slab 2 under steady state condition. This is the given in the problem, okay, this is given, this data is given. So, substitute 2 in 1 and simplify, you will get K1 is equal to 2 times K2. Okay, so, that is a very simple one. Next, the last problem pertaining to conduction heat transfer. 3 slabs are joined together as shown in the figure. The center slab experiences a non-uniform internal heat generation with an average value equal to 10,000 watt per meter cube, while the left and right slabs have no internal heat generation. All the slabs have thickness of 1 meter and thermal conductivity of each slab is 5 watt per meter Kelvin. So, K value for all the slabs are constant, thickness L value is also constant. The two extreme faces are exposed to fluid with heat transfer coefficient 100 watt per meter square Kelvin, and the bulk temperature is the fluid temperature 30 degree centigrade. If the left extreme temperature is 100, estimate the right extreme temperature. So, this is what you have to find out. Okay, so, the fluid temperature is given, heat transfer coefficient on both sides is same, thickness of the layers are same. Okay, so, here I would like to emphasize on one thing. See this, when we say there are 3 terms Q is rate of heat flow, okay, rate of heat flow, rate of heat flow in watts, okay, in watts, or it is in joules per second, Small q, when I say, it is nothing but capital Q by A, that is heat flux, Q is in watts, A is in meter square. So, the unit will be watts per meter square. And when I say internal heat generation, I am using the symbol Q dot. So, this is heat transfer per volume, Okay, so, the unit is watt per meter cube. So, you should be very clear with this one. Q is the rate of heat flow, which is in joules per second or watts. Q by A is called the capital Q by A is equal to small q, which is heat flux, heat transferred per unit area. And whenever we are given the value, the data watt per meter cube, it refers to internal heat generation, that is heat transfer per unit volume. So, these 3 should be very, very clear. So, now at steady state, so this will be Q dot, So, here in this problem, it is given that there is if you look at the question, internal heat generation. So, this is given as per meter cube. So, it is Q dot, okay. So, it is Q dot is equal to 10,000 watt per meter cube. Okay. So, at steady state the amount of the heat internal heat generation, because it is per unit volume multiplied by the volume will be equal to convection for the first slab and convection in the second slab. Okay. So, at steady state this is internal heat generation multiplied by the volume equal to Q convection, let me write it clearly, Q convection slab 1 plus Q convection slab 2. Okay. So, this is the concept. So, this volume is nothing but area into length, okay, area into thickness. So, all the values, if it is not given, we can take A equal to 1 meter square and L equal to 1, okay, A equal to 1 meter square, L is equal to 1, and find out T2. How to write this one? This is nothing but based on the Newton's law of cooling, H into A into delta T. Delta T is from, okay, delta T is, see, if you see this one, this is the from we have to find out T2. Okay. So, it is from T1 to T infinity, okay, plus H into A into T2 minus T infinity. All the values are known, okay, all the values are known. The only unknown is T2, the only unknown is T2. Okay. So, all the values are known. Heat transfer coefficient on both the sides are same, it is 100 watts per meter square degree centigrade. So, you will get T2 as 60, T2 as 60. Okay. So, this is about this problem. Now, let us focus on the numerical questions. So, with this I have solved all the numerical questions in the previous lecture number 26. Now, let us quickly solve the problems in this lecture 27. Heat is being transferred by convection from water at 48 degree to a glass plate whose surface temperature is 40 degree. It is exposed to water. The thermal conductivity of water and glass are given. Assuming a temperature gradient of the water glass interface to be temperature gradient, that is dt by dx, find the heat transfer coefficient. Okay, find the heat transfer coefficient. So, here Q convection of water is equal to Q conduction of water. So, that is the concept. So, water temperature is given, glass temperature is given, water temperature is 48, glass temperature is, I think it is 40 degrees centigrade. K value for water is given, K value for glass, G refers glass, W refers water. So, convection we know HA delta T, conduction is Ka dt by dx. Okay. K into A into dt by dx, K of water, K of water. So, here you have to substitute the K of water. If area is not given, you can take 1 meter square, calculate the value for unit square meter area. So, we can find out substitute the values, all the values are given, okay, all the values are given. Of course, A will get cancelled in this case A will get cancelled. Okay. So, we can cancel this one or it will be for 1 meter square. So, if you calculate the heat transfer, sorry, this is not given, this we have to find out. dt by dx is given, dt by dx, that is the gradient is given. This is dt by dx, 10,000 Kelvin for every meter, 10,000 Kelvin for every meter. So, that with this we can find out these terms will get cancelled. In case if there is only one term in any other equation like q equal to HA delta T or q equal to minus Ka dt by dx. If A is not known, we can find out area. Okay, we can find out area is 1 meter square. Okay. So, the heat transfer coefficient is 750 watts per meter square Kelvin. Okay. So, that completes, we have to find out the heat transfer coefficient, the value of H. So, Q convection by water is equal to Q conduction of water. Water flows through a tube of 3 centimeter internal diameter and length is given. Okay. So, diameter is given, length is given, diameter is 3 centimeter, length is 20 centimeter. Meter. Okay, so the diagram I have given. Inlet temperature is given as 10 degrees centigrade. The outside surface of the tube is heated electrically so that it is subjected to uniform heat flux circumferentially and subjected to uniform heat flux. The mean inlet and outlet temperature of water are given T1 and T2. T1 is inlet, we are taking 1. So, inlet temperature T1 is equal to 10 degrees centigrade, outlet T2 is equal to 70 degrees centigrade. Okay, heat transfer coefficient is given, mass flow rate is given 720, mass flow rate of the water is given, heat transfer coefficient is given, H is 1697, H is equal to 1697 watt per meter square Kelvin. Mass flow rate of the water is given, so this should be m dot. Okay, this should be m dot. M dot is equal to 720 kg per hour divided by 3600 to convert to kg per second. So, we will get 0.2 kg per second. Okay, 0.2 kg per second. So, write the energy balance. So, if you I have converted the given data into a form of schematic. This is the water is flowing from this one inlet to outlet. This is the length of the tube. There is a constant heat flux which is applied. Okay. So, uniform heat flux. So, if you write the energy balance Q into A. So, heat flux is capital Q by A, capital Q by A. Let me emphasize heat flux is equal, heat flux is small q equal to capital Q by A. It is watt per meter square, not meter cube. Meter cube is only for internal heat generation per cubic volume. Okay, energy balances. So, if you see this one, the uniform heat flux, that is Q into A, will be equal to mCp delta T, mCp delta T. So, energy balance is Q into A is equal to mCp delta T, mCp delta T. Okay. So, here it is m dot, let me due to the compatibility. Okay. So, it is not Cp of water we know 4.18, substitute the values, T2 is given 70, T1 is given. Okay. So, we can find out the Q value, we can find out the Q value. So, that will be 26.7 kilowatts per meter square. So, you can, using this formula you can find this Q value. All the values we know, mCp delta T, m dot is given, m dot should be substituted in kg per second. So, we are getting Q as 26.6 kilowatts per meter square. Okay. And now apply the Newton's law of cooling. Okay. Apply Newton's law of cooling, Newton's law of cooling, Newton's law of cooling. Q equal to H into A into delta T. If you bring this A to the left side, it becomes Q by A, which is equal to H into delta T. This Q by A is nothing but small q, okay, H into delta T. We know the value of Q, we know the value of H, H is also given. Delta T is temperature, we have been asked to find out the inner surface temperature, find the inner surface temperature at the outlet of the tube. Okay. So, delta T will be equal to, so this is equal to H into temperature at the outer surface of the tube minus T2 minus T2. Okay. So, if you take this formula, Q is known, we have just estimated, H is given, this is unknown, T2 is given. So, we can find out the temperature of the tube. The temperature of the tube will be equal to 86 degree centigrade. Okay. To be more specific, it is 85.7 degree centigrade. So, first write the energy balance. The heat flux into area is equal to the heat gained by this one, by the fluid, that is the water, mCp delta T, mass fluid of the water is given, Cp of water is given, delta T of water is delta T, T to 70 minus 10. So, all the surface area, apply the surface area pi dl, okay, that is 2 pi RL or 2 pi RH, and apply the Newton's law of cooling. Q equal to HA delta T, Q by A is nothing but heat flux, small q, which we have calculated, H value is given, delta T is tube outer surface temperature minus the T2 value, which is given as 70. So, if you substitute, you will get the answer. Okay. Next one is a cylindrical uranium fuel rod of radius 5 millimeter in a nuclear reactor is generating heat at the rate of 4 into 10 power 7 watts per meter cube. So, this is Q dot. Okay. The moment you find this term, this one, watts per meter cube, it is Q dot, 4 into 10 power 7 watts per meter cube. Watts per meter square is small q, heat flux. Watts per meter cube, we are using the letter Q dot. Radius is given as 5 millimeter, R is equal to 5 millimeter, 0.005 meter. Okay. H is given as heat transfer coefficient. The rod is cooled by a liquid whose temperature and heat transfer coefficient are 25 degrees centigrade and 1000 degrees centigrade. Okay. So, the temperature is given as 25 degrees centigrade and heat transfer coefficient is 1000 watts per meter square Kelvin, 1000 watts per meter square Kelvin. Okay. And I think we have written all the data. Once you know the radius, we can find out the diameter, okay, that is twice the radius. Okay. So, now here also energy balances Q into, because this is internal heat generation. So, Q dot into, so let me write this is Q dot, okay. So, this is Q dot, Q dot into volume is equal to, if you energy balance, amount of heat energy generated internally into volume is equal to Q of convection. So, this is equal to Q dot into, okay. Let us take the thickness, okay, volume of the rod, pi by 4 d square L, okay. Let us write it, pi by 4 d square L, pi by 4 d square L. So, that is the volume of the cylinder, that is equal to Q of convection, H into A into delta T, and we have to find out the surface temperature, estimate the surface temperature of the rod. So, here it is the volume of the tube is nothing but a cylindrical component, okay. So, pi by 4 d square L, so that is area into L. So, this is nothing but Q dot into pi by 4 d square into L equal to H into A into delta T is surface temperature minus fluid temperature. So, now using this one we can find out the diameter. Diameter is equal to 2 times radius, 2 into 0.005, 0.010 meter, okay. That is 10 millimeter, radius is 5 millimeter, so diameter will be 10 millimeter. So, all these values are known, okay. Let us see what is the value of L. I think the length of the pi by 4 d square L, okay. This length term will get cancelled. So, this is H into surface area pi dl into Ts minus T infinity, okay, pi by 4 d square L. We can even simplify this one. So, here I am using pi dl, let us use as uniform letter, this is small d, this is small d. So, these terms will get cancelled, length will get cancelled, one diameter term will get cancelled. So, you can find out Ts. This value is given, okay. H is given, T infinity is given, diameter is given. So, we can calculate the surface temperature, it comes to 125 degrees centigrade. 125 degrees. So, if you see these problems and all, so this problem, like apply the energy balance. So, in this one the Q convection of water is equal to Q conduction of water, and in this case there is a constant heat flux which is applied. So, that amount of heat, amount of energy is equal to the heat gained by the water, because that the water is taking that heat and it is getting heat, it is like heat loss is equal to heat gained. And then applying the Newton's law of cooling, we can find out the temperature of the tube. And if you take this problem, here the energy balance, is the amount of internal heat generation into the volume, that is equal to the Q of convection, HA delta T. Okay. In this case, the diameter term and length term will get cancelled, and in the previous case, okay. So, in case if A is not given, we can take 1 meter square, but when we have A term on the left side and right side, it obviously gets cancelled. Let us move to the last problem, okay, quickly. So, air at 73 degrees centigrade flows over a flat plate. This is based on the boundary layer concept. Plate of 1.5 meter length maintained at 27 degrees centigrade. Velocity of the fluid is 10 meters a second. Find the thickness of the thermal boundary layer at a distance of 0.5 meter from the leading edge of the plate. Leading edge of the plate is the extreme left. As the flow takes place, this is the leading edge and this is the trailing edge. Okay. So, length of the plate is given 1.5 meter. Velocity, this is not volume, this is velocity. We use small v for specific volume. Okay. When we write v normally v is for velocity and volume. So, let us specify velocity is equal to 10 meter per second, and temperature of the fluid is 73, temperature of the surface is 27, temperature of the fluid is equal to 73 degrees centigrade, temperature of the surface is equal to 27 degrees centigrade. So, this is flow over a flat plate, flow over a flat plate, flow over a flat plate. This is an external flow, that means it is an external flow. You have to find out the thickness of the boundary layer, thermal boundary layer, to find the thickness of the thermal boundary layer. Okay. Whenever we solve problems related to forced convection or free convection, or when we want to find out the properties of the fluid, it has to be found at mean fluid temperature. Properties are to be evaluated at mean film temperature, that is equal to Ts plus T infinity by 2. So, this is equal to 27 plus 73 by 2, that is equal to Tf is equal to 100 by 2, 50 degree centigrade, 50 degree centigrade. Okay. So, if you see this one, properties are to be evaluated mean film temperature. So, here it is, this is the HMT data book. Let me quickly explain. The properties are to be evaluated mean film temperature. From heat and mass transfer data book, I am using the 9th edition by this author, Godhan Raman, at 50, page number 42. So, this is page number 42, this is page number 42, corresponding to 50, this is 50. Okay. This is kinematic viscosity mu, since the letters are not clear, and this is Prandtl number PR. So, I am reading this value. So, this is I think 18.97, 17.95. Sorry, this is 60 degree. Our fluid temperature average is 50. This is 50 degrees centigrade. So, read out this value and this value. Prandtl number is 0.698. So, that is what I have taken. Find out the Reynolds number. you will get 2.78. I have mentioned very clearly, if the Reynolds number for an external flow is less than 5 into 10 power 5, the flow is laminar, hence the flow is laminar. So, from HMT data book, page number 121, I have using the data book by C.P. Godan Raman and Subramaniam, the 9th edition. So, in case if the edition is different, slightly there will be changing the page number. So, this is the formula for hydrodynamic, this is page number 21, external flow. Here you can see properties are to be evaluated at flame temperature only. So, this is the formula for hydrodynamic boundary layer, okay, and this is the layer for delta T, this is delta. They use the term delta H, hydrodynamic boundary layer, and if you substitute and you can find out this one. Okay. So, let me conclude. In this lecture, we have discussed about the convective mode of heat transfer, the different types of convection, natural convection and forced convection, how the concept of boundary layer, what do you mean by velocity boundary layer and thermal boundary layer, and we have solved some numericals pertaining to convective mode of heat transfer. With this, let me conclude this lecture. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar, and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.